everyone. Welcome to the new edition or new meeting of West Coast Machine Learning Group. So today we are planning to go through the consistency models, the models that came from the same group and person who was the main force for the score-based generative models, which is the backbone of diffusion models. In this meetup, we have gone through several meets in the past where we went through the score-based generative models. Specifically, we went through the video from Yang Song, which covered the score-based generative models. We went through the history of, well, starting from what score is and what is its relevance to the data distribution, to ability to generate score models, to generate a network that estimates the score and then leverage that score for generating the samples. Yang Song has been instrumental in several enhancements in that area, starting from first time the group used score and the denoising score matching algorithm for generating samples using score matching Langevin dynamics. We went through that also in our presentation. And then in around 2020-21, after the DDPM paper came out, which leveraged the same mechanism as the original diffusion model for the loss estimate for generating denoising and generating images from noise. After they leveraged or proved that the noise constrained score models, which noise condition score models, which were used to generate the samples. The objective for those was similar to the objective that was used for the denoising algorithm for DDPM paper from Jonathan Ho and others. Inspired by that correlation, Yang Song and team went ahead and formulated the denoising using the stochastic differential equations. So with that little background, this is where we'll start from today and kind of have a little bit of reintroduction to the SDE and ODE formulation of the sampling, if you may, in the diffusion process, and then from there go to consistency models, and that kind of lays the background for where consistency models come in. Now, with that background, let me also highlight well, maybe when we go to the slides, we will anyway cover much of this. So let me share the screen, and please let me know if you're able to see the screen. Since I am presenting from the laptop, I may not see people's faces and the chat. Sorry, I'm presenting from the iPad and not the laptop, so I would appreciate if someone can help me with that. All right, so let me start the screen share here of the presentation that I have. All right, are folks able to see this?
Yeah, got it.
Okay. So there was another meetup group where I made this presentation, so created this deck for that group. I know that there's a recording for that meeting as well, which can serve as the precursor for this meeting, but I don't think I have access to that recording, and also I don't know if we have permissions from everyone who attended that meeting that it's okay to post that recording. Nonetheless, I will make this presentation available to everyone, so people can view it and can, of course, feel free to reach out to me or for any questions that you may have for the material that I'm not going to cover here. So this presentation did go into details of the portion of, or the journey before stochastic differential equation based diffusion models. So I'll skip past that. So the title here was from score models to diffusion models to consistency models. All right, so the slides are based on these sources. There's a great video by Yang Song on YouTube. His blog also covers a pretty good deal of the material that we see here. There was a Stanford professor, Stefano Ermon, has a great presentation on the score matching part of it, and the original Langevin dynamics-based generation model, image generation model. And then for the consistency models, I have relied also quite a bit on Yang Song's NeurIPS presentation in 2023. There may be more which I've reviewed, but I may not have put all the details here. So with that, I will skip past much of these slides, which we have covered in different meets here. We can come back to it as needed if there are some questions. So one of the key things that, let me see if there is a good slide to kind of highlight that. Maybe I'll just skip past, that's okay. So one of the key things that Yang Song wanted to highlight based on the score-based generative models was that those models provided the flexibility of leverage the full flexibility of the deep neural networks while removing the dependency on the normalization constant for the probability distribution for your data set, and as well as be able to give a very good likelihood estimate. So what we see here with the stochastic differential equation formulation of the denoising or the generation model, what we'll see is the likelihood estimates being very good, and that's what is being then used to improve the speed of generating the images from the models. Now, I kind of spoken quite a bit of cryptic language, assuming that audience here is aware of what score-based generative models are. So maybe I'll just pause here for 10 seconds in case anyone has a question or comments or concerns before I proceed.
Do we have access to the slides?
So I know that it is open, but let me see if I can share that, or if Roger or Ted, if you have access to this, are you able to share that?
Yeah, what I think what we'll do is we'll post it on the Slack, links to it. And if you're not a member of the Slack already, I'll put a link in the chat here. You can follow and join our chat, our Slack channel.
Perfect, thank you.
Okay, so what is, just kind of going into the theory of diffusion models, what exactly they do, and how do they learn the probability distribution of the data sources. So essentially, there is where you start from is you have the original data distribution. In this case, this is a toy distribution that is taken for, let's say, a bimodal, or in this case, a mixture of two Gaussians. And what you see is that you inject the noise, which is you perturb the distribution, and if you have few discrete steps, the more noise you inject, the goal is to, the target is to land at the perturbed distribution, which is a single Gaussian of a distribution like this. And overall, what you prefer or want to do is you keep on increasing the perturbation, and right now it shows 4 steps, but you can have 8, 10, 20, and so on and so forth. But and what you see over here below is the one-dimensional heat map that represents the noise densities or the distribution densities, and essentially corresponding to the noise that is injected. And as you inject more noise, and if you make it the step smaller and smaller, eventually it will become a continuous noise injection, and you could think of that as the a continuous time noise injection mechanism, where that 1D map over here becomes the 2D map as you see over here in this image below. And what you see is, as I said earlier, this is like say mixture of Gaussian with two Gaussians. And as you inject noise, you land at a single Gaussian, where at the time step varying between 0 and uppercase T, at time step T equals 0, this is your original data distribution. And at time step T is complete noise, and which is very close to the Gaussian distribution. So this is a typical problem formulation or the noise injection. And what is done here is that, if you recall in the original diffusion, you have multi-step noise injection, but with the continuous time formulation, it is a continuous noise injection. And this is essentially, perturbing the data with stochastic process. So you're using the stochastic perturbation to convert the data to noise. So you start from the initial clean data, what you see, these 4 images here, for example, and you progressively are injecting the Gaussian noise in it. And as you inject the noise, at the end of the perturbation, you get basically Gaussian distribution. And this is the distribution, as you can see, these for 4 different samples, they have picked up where the original points were, and they, with the continuous noise injection, they land at, over here in some distribution around here. And I have a small notebook. I don't know if I'll be able to present that, where I just scaled it to hundreds and thousands, and just to see how it proceeds, and then also look at the distribution of the final thing. Of course, this is Gaussian, so there's nothing special about that. So the trajectory of these data points is basically, you can view that as the trajectories of the stochastic process. And in this case, it is a process with a collection of finite random variables, if you may, because when you go in the continuous time, any time that you look at, it's a random variable. So it's basically a collection of infinite random variables at any point in time. And the random variable at any time step that you want to look at, the corresponding probability density is the distribution of the data points. And that is called, I think, the PTX. So basically, that's the probability distribution of X after injecting noise and looking at it at the time value T. And T, of course, as we know, is between 0 and uppercase T. And this is this process can be solved using the stochastic differential equation, where you have 2 terms. This is the typical formulation of the equation, where the first term is the deterministic drift, and the second one is the Brownian motion with the diffusion coefficient, and this is the Gaussian noise that you're injecting at every time step. This is the Brownian motion, essentially. And this is the stochastic term, basically the noise, and this equation, or this stochastic differential equation, relies on this noise. And what you have here is the simplified version, which is what I think they end up using for the simplification, but I think the intuition carries on to the complex one also. So this is what we have in terms of, so this was injecting noise, right? The forward process, as it is called in the diffusion process. And what you have here is the reverse process, where you have denoising. Essentially what you see here is if I go back very quickly to show the stochastic process, where you have the bimodal distribution on the left going into Gaussian. And what you have now here is the Gaussian distribution on the left, and you're doing the reverse stochastic process, and I'll come to why it is the reverse stochastic process to get the bimodal distribution here. So, and what this is used is, of course, to generate samples in the diffusion process. So you start from the Gaussian noise, and you have a reverse sampling process, which gives the noise-free samples or the approximate sample from the original data distribution. And the thing about these two stochastic processes that if this is your forward SDE, which goes from 0 to t, the reverse SDE is also, the reverse stochastic process is also an SDE, which is dependent on the same parameters, but includes a score function in its formulation, and is also a Brownian motion if you look at the infinitesimal noise in the reverse direction that is added. There was another video where one of the co-authors had two videos playing side by side, and what the point he was trying to make was that you cannot tell which one was the forward and which one was the reverse process. This was for the Brownian motion, not so much for the images as you see here. And the motivation was to help people get better intuition about how the forward process and the reverse process are both SDEs with the similar Brownian motion formulation. So the only other thing that is there is that this was, if you remember, the simplified version of the forward SDE. So this is the change in your XD with this noise and this diffusion coefficient. In the reverse one, while you have the same process or the factor here with a W bar T, but you also have the drift factor, which is dependent on the diffusion coefficient. So this is what I think Yang Song helped through, or maybe actually there is some paper from 1980s where they showed this. So now that we understand the forward and the reverse process, how is this trained? So the way that training is done is that you have this a neural network where you essentially are at every time step you have one score matching loss for each time instance t. So as you are going forward, going backward, you basically are estimating the score function for every time step, and the equation for solving the reverse SDE, which is same as from the previous page, as I said earlier, is dependent on this, and if I may go back, is dependent on this factor here, which is the score function, and that is what we had gone into deep in the previous presentations. So, and let me just make sure. So maybe I'll just spend another 10 minutes or 5 minutes on this and then go to consistency models. So we have the time condition score model. So we have the time over here, and basically what we have from our network is first we have the score function, and which gives us the model gives us the estimate of the score function, and then we use that to estimate this is the objective that we are refining for every time step. For any time step picked randomly between 0 and uppercase T, we are trying to optimize for the score, which is the actual score of the data, the score at the time step T with this probability distribution, and the one that model is predicting. And this is the objective function that we want to optimize for. And instead of building, because it's a continuous time function, so T is a positive weighting function that is used for facilitating the optimization for a time step. And I think it is sigma square is what they use. Sigma is, as you recall, the variance of the noise of the diffusion coefficient, which is a noise schedule that they have. So again, we had looked at that in the past, but just wanted to quickly present here that this is the objective that is optimized for. And when you are sampling, actually, before we go to sample, one quick thing is that this is still the SDE formulation that you have for sampling. So once you estimate the, once you get a good objective, once you get the good estimate for the score function, or your model is predicting the score, you inject that in this equation to sample when you're going in the reverse direction at each time step. And in order to sample from this, once you inject this, there are SDE solvers that help you get, solve for it and get the output. Again, I'll just pause here in case there is any question. Okay, so okay, maybe I wanted to read from the web page, but maybe I don't have it. So continuous time SDE to discrete sampling step conversion. So this is oh yeah, basically on the next slide I have the link. So in case you want to read more about that, you can do that. But this is the sampling. Actually, it is everything. So you basically, what I said in the previous slide, you have the time dependent score model that you are estimating. Then you are training to optimize this for this objective, where you get a good estimate for your score dependent on time step, and then you plug that into the reverse SDE to get the estimate of your delta X, and then you plug it into you leverage the Euler, one of those SDE solvers. So for SD, like in ODE scenario, you have Euler solvers. In this case, like Euler, Mariam, and I don't have too much of knowledge about that. People who have more know-how about this will know how it does that for the SDEs. But as you can see, there is a stochastic factor here. Depending on the time step, delta t, there is some sampling that is going on to get you the X at the time step t. So this is how you sample at each time step. All right, so this was trying to sample. And again, if I just go back here, so this is trying to start from the noise. And then once you have the model for the S theta, for the score, you plug that in for each time step and then get the sample in the number of steps that you have for referencing here. If you start from the same noise, because this is SDE and you may have you have a stochastic factor here. So with an SDE, you will be getting a different sample from the data distribution every time, because you have a stochastic factor in your solver. And that is an important factor to remember when we go to ODE. ODE is deterministic. But before we jump to that, what Yang-Song contribution was in this case was to showcase that the SDE formulation that we had, there is uh, 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 one-on-one, one-on-one correlation between the SDE that you have for your stochastic process to the ODE corresponding to that SDE for this kind of problem formulation. And essentially, what is the key thing that is showcased here is that like how we have the conversion of data to noise using SDE. This can also be done using ODE, and what he calls here is the probability flow ODE. So the ODE trajectories, and then let's just look at it a little bit closer. So for any of these original samples that you had, in this case, I think now they have 6 samples. You see for the orange, whatever color, red color, let's see, it goes and lands here, but you see a corresponding ODE trajectory, which is going like this. And what you have when you have ODE is deterministic, and for any time PT, it is a single value, as you see here. That single value for that point time t corresponds to the distribution for this red point with the SDE based stochastic process based noise injection, the distribution of that point over here. So the mean of that distribution is what this ODE trajectory point will be at this point in time.
Yeah, so
Yeah.
Dave, can I jump in?
Yeah.
Yeah, so what we're saying is that this is a stochastic process. So if you just add random noise, if you think of this as Brownian motion, if you repeat this, you're clearly not going to wind up in the same place every time, right? We're not saying the stochastic process is somehow magically deterministic. No, you're going to wind up in a whole bunch of different places. But what we can say is that there is a certain probability distribution about where you're going to wind up. And so we have an ordinary differential equation that will give you the exact same probability distribution of where you will wind up based on where you started without anything being stochastic. So like in a super ridiculous example, if you like flipped a coin, and it was a fair coin, and every time it was heads, I gave you $1. Every time it was tails, you gave me $1. If it's a fair coin, on average, they're going to cancel out. So like that's a ridiculous example, but I could like deterministically tell you that the distribution looks like some Bernoulli distribution or whatever, with the mean being the exact same amount of money that you started with. So yeah, any individual trajectory where you flip the coins, you're going to wind up with a certain dollar amount. But I can tell you in advance what that probability distribution is going to be deterministically without ever having to do any of the stochastic stuff. That's kind of what we're trying to get at here. And so if you know what that distribution is, where Dave's going to go next with the slide presentation is we can get rid of the stochastic equations. We can just use only the deterministic ODE equations. I hope that helps.
Yes, thank you, Ted. And I think Jerry or someone, you had another question?
Dave, just looking at the white line for the probability flow for the ODE, it's bent. Is that purposely done or just badly drawn? Can you see that?
You mean there is a trajectory for that flow?
Yeah, it seems to have a trajectory downward and then it comes back up, and it's kind of the mirror side on your second distribution. And
On this side, right?
Yeah. Is that significant or is it just, an artistic thing?
So if you look at the, let's say you have set of data points from your original data distribution, right? And if you look at after the SDE flow, where they land, right? So what you see, each one of these white lines at any point t, right? So what you see as bent or whichever way you want to describe it, right? So that essentially represents the distribution according to this PT. And if you recall PT, if I may go back to the previous slide, so PT is nothing but the probability density at any time step t. So if it is stochastic, even though, every time you start from this point, in this case, of course, it's repeating GIF, so it is showing it's going in the same direction. But as Ted also mentioned earlier, you start again, the SD is stochastic, so it will be in a different direction. But if you were to look at the distribution of that, and what you see, the ODE there represents the distribution according to this PTX. So that's a single point to represent the overall distribution for that sample at this point t, this time t.
And I guess what I'm questioning is, if we go back to this drawing, that single point, and is it just the way they drew it, or does it really have this kind of like converging type thing going on in the center and then diverging?
So it will,
when you read.
Oh yeah, so it will.
Yeah.
Yes.
Sorry.
It will have that. Oh, sorry to keep interjecting you. So it will have that, because essentially this bimodal has to map to here, right? And you look at this red point.
Model, right? Yeah.
Yes. So first time it showed here, second time it will show somewhere here, and so on and so forth. But overall, if you look at the distribution of every time you started from here, just this one, and did the SDE, and if you plotted for every time step where it was in terms of the representation of that multiple iterations of just this one red point, right? Then this is the distribution that you will see it flows with. Okay. So yes, it will follow that, assuming as infinite, or your number
typical
of
assumptions, right? Infinite,
so the
series,
head, tail,
whatever.
Yeah. So the same head tail example that Ted mentioned, right? So if you did it only 5 times, it will not show that, not be fair coin, let's say, right? Because or 10 times also, right? You may have 6 heads and 4 tails. But if you did it 100,000 times, then the ratio is close to 0.5, and then what that would represent is the flow from let's say, and in this case, you can assume that the stochasticity of coming to this is you're starting from some kind of, let's say, drift you have or whatever, right? In the beginning, you have some thing that affects your coin to be more head, right, let's say, right? And as you are moving towards this, you expect it to be close to middle, and that's because of whatever as you're injecting the noise, you're whatever the process that you define for that is leading to here.
Yeah. So I have another intuition for this. Help me understand. But the way I look at most of these things is, assume you have a hill climbing algorithm or something like that, and you have 2 ways to get to the top of the hill, and then again you come down. There are only 2 ways you can come down, but the trajectory to go to the top of the hill has these small perturbations, but you have to be within the bounds of the trail to reach at the top, and then again come down as well. So that's the intuition usually I have with these kinds of things, climbing up and coming down. So I don't know if that's a fair assumption, but do you see what I'm saying?
Yeah, I do see what you're saying. The only thing that I would say is that there could be sometimes some climber who may decide to go way off, and may land up there.
Yes. So
on the
that's
hill, right?
yes,
But majority of them will follow some path and land here.
And that I believe comes from the restriction of the Gaussian basically noise, which doesn't let them kind of drift too far in the other direction. I've never built that intuition, but that's what I feel doesn't let them go off trail. So their goal is to reach at the top of the whatever the hillock, right?
Right. And the other way to put it mathematically would be that the noise that you inject, the likelihood of this point reaching over here is very, very low. It is possible, but it's very, very low.
Yes. Correct.
So,
correct. Thanks.
Yeah. So and maybe that's the term that I should have used all along, that this is the likelihood for the path that this red point is following, because that's exactly what the ODE ends up giving us, is the exact likelihood at for estimate for the data distribution, because it's a one-on-one, and I'll come to that. This is a one-on-one bijection, but so I don't know if I answered your question to your satisfaction, Jerry, but
yeah, I
this
think,
what it is.
yeah, let me think about it. Just continue. I'll think about it a little bit more. And
Yeah.
if I come up with anything, I'll interrupt you.
If I could try, Jerry, I think the short answer is it's artistic. This is a one-dimensional data example, right?
Sure.
Where you start with just a real number and it has two modes shown on the far left, right?
Mm-hmm.
And then you add Gaussian noise and it winds up with just random Gaussian noise with one mode.
Okay.
Exactly how they're bendy is not super critical. I think, Dave, you might have said that the white lines represent the average path for each starting point. I don't think that's accurate.
The likelihood path, yeah, okay.
What the white points do is they wind up at points with the exact same probability distribution as the distribution of stochastic paths from your starting points. But the reality is that every single point, the most likely outcome is going to be like right in the middle there. So if you see those like very top and very bottom white lines, that would never be the most likely path for any point. Okay. But what we get is just this beautiful one-to-one correspondence where for any given starting point on the left, we have a white trajectory. And if you look at the probability distribution of where all those white trajectories wind up, it's the exact same probability density as the stochastic paths. It just gets there a different way, but it provably has the same distribution. And ultimately, what we care about is being able to predict the probability distribution of our data. So we want that mapping from pure Gaussian noise to our data distribution. We don't actually care what kind of mapping it is. Ideally, you want something that's fast, but otherwise, you really don't care what kind of mapping it is. So whether it's stochastic or it's deterministic, and the reason why we go with the deterministic is we're going to see that it is faster and that it has some better properties.
Thank you, Dad. So one other thing of importance here is that when this one-on-one equivalence is established between the SDE path to the ODE path, then or SDE is of course a set of paths to the ODE, you end up getting the score function back in your formulation, which is super cool because with this we already have solved for the score function models in the past, and this is for the formulation basically that we have for our if you recall the toy problem that we have for SDE, right? If I may go back here again, here. So if this was the forward process, so equivalent to that, the forward process ODE is what you get here. So with that formulation, this formulation comes with a few more properties, and the key property that it comes with is that the ODE basically is so now we have removed the SDE from this one, and what we are showing is the reverse paths, only the right hand side of this. So if you look at and only the ODEs here. So what you have is the one-on-one mapping from the prior. So if you start with some noise and you have a sample over here, then there is a one-on-one mapping onto the data where that maps to. And it's also relatively efficient because now you can start with any noise and go through your steps using the ODE solvers to get the faster sampling from the diffusion models. So what you have at the bottom is also, as was saying earlier, that now with this one-on-one mapping, what you are able to do is for any data that you have, data source or data set that you're working with, you are able to get a very good estimate of the likelihood. And the PFODE, the probability flow ODEs, they allow they're saying their claim is exact likelihood estimate if you can solve for this. And I know that the trace of the score model is a difficult one, so because you'll do an estimate here, but still it gives you a very good estimate for your likelihood for your original data. So again, these are past works, not part of the consistency model, but this is also for going into the theory of how the ODs are used and solved for to generate the data from the noise. So let me kind of repeat that. So we have the diffusion process where we start from the data and inject noise and reach the Gaussian distribution. When we are generating samples, we use the Gaussian distribution as the prior, and we start from there and then use the ODE solver and individual steps to reach to the data that we want to generate. And this was the state of the art in terms of the theories that powered the diffusion models. There were many more things that came into the diffusion models after this paper from Yang Song. And without going into the details of those, we had EDM paper from NVIDIA that refined with various refinements of basically steps of the noise injection formulas and variance assessments and so on and so forth to get better results. And then of course the stability diffusion used, instead of doing the noising and denoising on the original image, it worked on the latent space and made it much faster. And so those were more enhancements, but this is the core foundational theories that power the current state of the art diffusion models. So now what the challenge, and then maybe we should come to the challenge. There's some more stuff which I'll not go into that. So now we'll come to consistency models. So yeah, we have another 35 minutes, so hopefully we can cover quite a bit of it, or maybe the whole of it, because the theories that lead to consistency models is important before we go to solving, or looking into consistency models. Once having gone through that, consistency models are relatively straightforward, and the only thing that not the only thing, but the most important thing that we need to understand or know about there is the distillation process, but that assuming that people are relatively more comfortable with, so consistency models become much easier to understand. So what is the core for the consistency models? The main motivation for the consistency models was the concern about the speed at which you generated the sample. So even with the advanced sampling techniques that I talked about, you still needed to do a lot of steps for generating reasonable images. And you needed to evaluate the score model multiple times. And if you wanted a good quality image, as I said, at least 20 steps were needed, and often need thousands of sampling steps, which limited the real-time generation. So even if you had the advanced multiple sampling techniques, like, let's say the faster numerical ODEs, they would still require at least 10 evaluation steps. And each one of those ODEs also is, I think internally they have sub-steps, if you may, but let's not even go into that, how they do that. So what consistency models do is to tackle this challenge of starting from your noise to the data. And their premise is that be able to define a function, f theta, that you give it, for any trajectory that we saw for the ODE, if you pick the sample at time step t, that should, in single step, this f theta should map. So in this case, for example, at time step small t, this sample, it should take you directly to the original data instead of going through the sub-steps that we have in the original diffusion models. So this is
can you repeat
what
that?
consistency.
Yeah.
I lost you
So
on
what?
that, so.
No worries. Yeah, I was not very consistent with the definition. So what you have in the original diffusion models is you start with the noisy distribution, right, prior, and then in each single step you are getting a denoise step depending on the number of steps that you have trained it for, and you remove the noise at each step and come to and get your original data during inferencing or during sampling, right? What consistency models are trained for is to identify that function f, that for this trajectory where you have this noise, right, pick up any like this noisy sample, it will in single step, once you have learned your function f, in a single step, it will take your noisy image to the original image. So irrespective of, and then the way it trains that, I mean, showing these steps, sub-steps, but let's say if you were to pick a noisy image at time step t prime, and that noisy image is xt prime, which corresponds to the original sampling path. Wherever you are in a single step, it should be able to give you the original image x0. So that is what consistency model trains, is this function f theta. That, and if I may go back to that original here image here. So let's say if you started from this point, ODE solvers in the denoising diffusion models will, or denoising diffusion model in every step will use the ODE solvers and the score estimate for that timestamp to take you to this point here, right? And what consistency model will do is you start from this point, and in a single step, it will bring you there. And the theory or the reason it wants this function f theta is being learned for consistency models is relies on the core factor that there's a one-on-one mapping between the noise and the theta. What you saw, those other noisy denoised images on the path, is just to show that that this function f theta is learned such that depending on any time step, if it is on this trajectory of ODE, let's say this line is the ODE line, then wherever you start from, it should always take you to the original image or data point in a single step, as long as you know what time step t prime it was for your function f theta. So function f theta for any noise at time step t in one step should give you this. For a time t prime, if you have an image which, let's say, land was from on the ODE trajectory for this noise path, again in a single time step should give you the original image x0, and so on and so forth for others. And we'll go into a little bit more detail of that, but just very quickly wanted to motivate what the consistency model tries to do. I don't know if it fully answered your question,
Yes,
but
it did. But I had a subsequent question to that. I'm kind of thinking those are checkpoints at T prime and T. What happens if you're somewhere in between T prime and T? Do you have to go to T prime and then you take the fast path? Is that you'll cover, or?
So that's a good question. You don't have to, but if you want a better quality image, they have a multi-step sampling algorithm where you do, so that's on the sampling side, but you don't have to do multiple steps. You can do it in one step, but then their results show that in a single step, it did get you very close to the original data. There is still some scores, which like the scores are not the best, but if you take multiple steps, then your scores get really, really good.
Thanks.
Hey, Dave,
Okay.
can I jump in with a comment?
Of course, please.
Yeah, so earlier, Jerry asked the question. He said, okay, in our fake 1D example, we have these white lines, and it looks like they bend out a little, and then they curve in or whatever. That's exactly what we want the consistency model to learn. We want the consistency model to learn the general shape of all the white lines, so that if I give you any starting point, you're just like, oh, well, it's going to bend out a little, then it's going to bend in, and this is where it's going to end. And I can tell you exactly where it's going to end without actually calculating 20 steps in between. I can just boom. So you can give me any point, and I'm just like, yeah, okay, fine. And if you want to give me a point halfway along the white lines, I can actually tell you where that's going to end. But the one I really care about is the one from the far left, where we start with just random Gaussian noise, and I can, boom, in one step, predict exactly where it's going to land.
Thank you, Ted. Yeah, that's very helpful.
Hey, Dave,
Yeah.
ever a quick question, and defer it if it fits better later. But when this projection, this function f theta projects back to x0, is x0 going to be any image in distribution, or will there be some Gaussian noise still present?
That's a good question. So let's first do the reverse thing. So when we inject noise, right, we will land at from original data at some noise point, right? Now, when we are injecting noise, it is a stochastic process, right? You're injecting noise with that Gaussian noise in there. So your data points are limited, but your noise space is covering the whole space. So if one has to speculate that, hey, for any noise, will I always get a sample from the original data? Well, it will try to go back to the original data space, if you may, distribution, but it will be approximately in the space of the original data. So now, to answer your exact question whether there will be some noise or not in the original in the data that is generated, well, it is, we have the scores for that, FID and whatnot, to kind of measure how good quality it is. So in a single step, when from noise to the data that is generated, it does not beat the state-of-the-art generation models, but with a few steps, it is able to beat those and become the new state-of-the-art, especially with the new enhancements that they have put, which we are not going to cover in detail today. I don't know if I answered everything that you asked.
I think that answered the question. Thank you.
Okay, and I'm sorry, because I'm using my iPad, I don't know who asked that question, but that's okay. All right, so essentially we're trying to train this function f theta, right? So this is the goal of the consistency models, and what we want to do is to estimate the consistency function f, and in order to do that, there are certain properties of this function that need to be met by the network that is going to implement this function, right, or model this function. So we know that, of course, there is a one-on-one bijection in the ODE trajectory between the data points and noise vectors. So if this is how we started and this is the noise point, and to answer the question for the previous speaker, let's say if we started from here, yes, we should land here with, again, depending on how good our function is, but in vicinity of this. But if we start from this point and we didn't have any data point which mapped to here in our ODE trajectory, then of course, it will land somewhere, let's say in middle of this, which may not correspond to any data point. But coming back to this one here, so the things that consistency models need to, the properties that they need to satisfy are, or let me just read it just for completeness sake. So consistency models are trained to map points on any trajectory of the PFODE. So in this case, they have picked up, let's say, this trajectory to the trajectory's origin in one step. So f theta xt comma t equals x0. So x0 is this point here. So wherever you are on this trajectory, if you end up picking a point from there and you know what that t was, then it should always go back to x0. However, it needs to meet the boundary condition that when it is really, really close to 0, and epsilon is the starting point for, I think the convention in the diffusion models that this is the starting point of the first noise that you inject. So if you are using this function at the very, very starting point, then it should give you x0, and that is just to avoid the collapse into some value that you're essentially to make sure that when you are denoising from here, it always gets to your x0, at least for this trajectory point, very close to the original data point. So this is one condition that needs to be met. So that, which is like output should match the input when the time is 0 or very close to 0. And the second one, which gives the names consistency model, is the self-consistency constraint, that for any two timestamps t and t prime, for any two timestamps t and t prime, the output of the consistency model f theta, and t and t prime are between epsilon and t, of course, not 0, it is from epsilon to t, then this should be the same value, right, which is the origin essentially. And I mean, this is a given that this is a one-on-one trajectory, right? So this is what it is trying to learn. So if a model that is trained to satisfy these conditions, it becomes a valid consistency model. And boundary conditions are satisfied via the network parameterization. I'll show you soon on that one. And for the self-consistency property, those are enforced via the learning by picking up different points or consecutive points along the trajectory, and we'll come to that. So they have a couple of algorithms, and we'll come to both of those on how they train it. So this is what it's supposed to do. I'll skip this slide for the time constraints. So now coming to sampling, this question was asked a little earlier, that do we do it always in one step, or can we have multiple steps? So we can have both. We can do it in one step, in which case we start from noise, and in a single step we get some image. And as you can see, there is some noise, or this, when you, I don't know if I want to call noise or the quality of image, whatever you want to call it, right? So it's not the perfect or good quality image. But what you can do is that you can have a multi-step. So in the multi-step, essentially what you do is you get the image, and you start from noise and you get the image, and then you say, well, you know what, I will take it to time step t, and let me kind of go back to this image here. So I started from here, or maybe a previous image, much easier. So I started from here and I got some image close to x0 or some image, and then I inject noise. And injection noise, if people who know diffusion models teaches on how the injection noise, that's a single step analytical equation. So then let's say I go to this t prime, and now I want to apply f theta again and get x0 again. But now I'm giving it that, hey, I'm gotten an image which is a noisy image from here at time step t prime, and then when I pass it through my model, then it should give me back x0. And if I do it multiple times, 2 times, 4 times, my images get much better. And I think they had results, which if we can get into it today, in 2 steps, they got pretty very good results already with 2 steps, and with 4 steps or more, with some more improvements that are applied in consistency model since then. They are, I think, again, state of the art. So
Hey,
does
Dave,
that
can I
help?
make a quick comment?
Yes, yeah.
So the reason why this works is relatively intuitive, is if you need to, in one single step, in one fell swoop, predict what the original X0 image was, the closer you are to an image, the easier job it is. You start with complete full Gaussian noise. It's really, really hard to predict what that image was. But in the second step shown on the right, it's like, oh, okay, yeah, it's a dog. It's kind of a little bit noisy, but it's dog. So, our time t is maybe like 1/10, of the way to big T, right? So as long as the neural network that we've trained is better at predicting trajectories when you're close than when you're far, then this technique will work, because basically you add less and less noise with each iteration. And so then it has an easier job to predict something that's fully in distribution. Remember, there's no right answer. It's a generative model. You just need it to be in distribution. You need the dog not to have 3 eyes. You need the hand not to have 6 fingers, or maybe the kinds of mistakes it makes would be a little more subtle, like people's eyes generally are the same color and they're kind of one-ish color. They're not like green iris on the right half and blue iris on the left half, right? So that maybe is a kind of mistake that you might have some modeling of a different color in the iris, but you add noise and you denoise it, and then it's going to probably fix that because it's going to pick something very in distribution.
Thank you, Ted. Yep. So this is the algorithm that I just described. You have, if you're doing multi-step consistency sampling, then it's from the paper. So you get the initial noise, and then you first get the initial origin point by applying your consistency model. And then you repeat it. In this case, they have a total of n steps. So of course, first step got you X, and then for the remaining n-1 steps, they are picking some noises. This is the Gaussian noise that they add, but depending on the time step that they have, and they're going from higher time step closer to the original time step, 0 time step, if you may, right? So, and xt is of course the far right noisy total Gaussian noise. So they are going closer and closer to the origin, and every time they apply, they sample the image by applying the noise to it. And by the way, this is the analytical equation to just get your forward noisy equation at time step t_n, and then you apply your model again. This is your new X, and then you do that till you have applied, in this case, uppercase n steps. So how do they enforce the boundary conditions on the model? So what we saw here was a sample, right? We still haven't looked at the training part. And in the training, they have to learn this function f theta, which is going to meet these boundary conditions, right? So these boundary conditions are not going to be met by the unit architecture that we have in the typical, denoising or diffusion models. So what you have here is, so if this was your denoising model, what you're trying to do is to add some skip connections to it, so that your f theta is essentially a function of what is output from your model or a skip connection. And this is a simple trick which is used even by the other diffusion models. There's nothing new essentially. So if you are at epsilon time step, then your C skip is 1 and C out is 0. So which means you will output this. And if it is not, then whatever your network outputted is your f theta. And then of course, this is what you're training so that your boundary condition is met. There's nothing special about that. This is very straightforward. Just how they enforce the boundary condition with this skip connection, where you have C.
Is that
yeah.
Is that an approximation, or is that kind of I don't know how to describe it, an impulse function or a switch that's only true at epsilon?
So when you say approximate,
yeah, 2 epsilon is C out equal not equal to 0.
yeah. So C out will be, so what will the value of C out, whatever is, so this is also, I think they learned this also, except that this is the value that they have.
But
Is
it's
that
not
your
like
question?
a switch.
Sorry?
It's some sort of smooth function.
Yes, it is. Yeah.
Okay.
I think that's what it was, and I'm trying to let. I mean, I can go back in the paper and look at it, but
So I haven't looked at the code, but what I'll say is epsilon cannot just be this theoretical super tiny number. It has to be something that actually occurs during training. Okay. So
oh,
we
if that's what
need,
your question is, yes, yes.
yeah, we
Go ahead.
need we need the there to be a certain number that's not too tiny of training runs where it actually is using time epsilon and that the skip connection is turned on, because that's how we enforce that the prediction of the model just equals the input for some really, really small times.
Yeah, so I guess my
and
question
if
is C skip equal to 1 only when T is epsilon, or is it smoothly approach that as T approaches epsilon?
Like I would think, I don't know how they implement it. I haven't looked at the code, Roger. I would think
Okay.
the answer would be time is less than or equal to my epsilon, right? So if you're sampling, because if you literally said epsilon is floating point 1, times 10 to the minus 8th, and in their thing, I think they said sample from epsilon to big T or whatever, right?
Yeah.
You're never going to actually get 1 times 10 to the minus 8th, whatever I said. You're going to get close, but you're never going to get exactly that. In that case, you will never actually see the skip connection turned on.
No, I understand, but you're still
So it can't
describing
be
it
that.
something that isn't smooth. It's more of a binary. It's either 1 or it's 0.
So
yes,
there is a
yes.
definition in the paper. Sorry to interject. On page 26, and I'm trying to load it here, and that's what I have on my big screen here. But if you go to page 26, they did define the function C skip.
Yeah, and Dave, it's just 1 or 0, right? There's no 0.9, there's no smooth in between.
For epsilon, but then it is for time steps greater than T, it's a function. I mean, of course, it's almost close to C skip is almost close to 0, or C out is almost close to 1. The other way around when it's not epsilon.
Okay.
Wait, aren't you guys saying 2 different things? Ted, if I understood what you said, you saying it's it could be not 1, right? It could be close, but or was that Dev? One of you guys is saying it's binary and the other one is saying it's not. So
Yeah. So I don't know for sure, Dave. Are you saying that C skip and C out can take floating point values between 0 and 1, or are you saying it's either 1 or 0?
So based on the definition that I see on page 24 top, and unfortunately, I tried to open it, but it didn't open it for me here, as you all saw.
That's okay.
Oh, now it works. I just had to press on my iPad a little harder.
just put your finger all the way through the screen. Works for me.
So, yeah. And by the way, this is just a small part of the paper. So the other algorithm is the bigger part. So while it's loading, we can come back to it if that's okay with people.
Sure. Sorry.
Yeah. And so that was just the boundary condition, right? And it is, we'll look at that. But the bigger part is the self-consistency. And there are two algorithms that they have defined for self-consistency. The first one is the distillation. And what you have for, like, it is an approximation, of course, but it in the distillation approach, they start with a pre-trained diffusion model and apply distillation to it, where they use the numerical ODE solver to define, of course, all the trajectories in the pre-trained diffusion models. So you already have a pre-trained diffusion models which can define for you the trajectories, and then they basically leverage that to define your function. And to enforce the self-consistency, what they do is they select two adjacent points, and then if you recall from the definition of self-consistency, the f theta for those 2 points should be the same origin point x0, and the objective is to minimize this. So once again, you have your pre-trained diffusion model. From that, you have access to the trajectory, and then you take successive points on that trajectory and minimize this objective function. And you do a random sampling, let's say at any time, you first sample time, uniformly sample time t prime, get the random sample by applying the noise to the origin to get your xt prime. And then you have the access to the ODE solver from the diffusion model. So you take one step and come to xt. And overall, the objective is to learn this function f theta by minimizing this objective.
Yeah, so
And
if I could say that in one sentence, right? We pick 2 points from the ground truth ODE solver's trajectory, and we calculate the L2 loss between the predictions on those 2 points. In a perfect world, they should predict the exact same x0. And then, as Dave said, you can have mode collapse. So then the model could just learn, always predict all zeros, and we'll never have any L2 loss. But that's where the skip connection comes in, because for a really, really small time step, it's going to predict the image. It won't predict all zeros, and then you'll have a massive loss. And that's what prevents it from doing that mode collapse, predict all zeros trick.
Yeah, and then I mean, there's a lot of math in the paper where they try to prove that the objective function is kind of equivalent to the diffusion distillation objective in the appendix A1, A2, and so on and so forth. But of course, we're not going to cover any of that. I don't even understand all of that. This is the algorithm in words, and this is the algorithm from the paper. But let's maybe go through the words. And by the way, what you see, the slide is not what I made, but I borrowed from Yang Song's presentation at NeurIPS. So given a pre-trained, I made the deck, but copy the slide from there. Given a pre-trained score model for the score function based on your data and time, pick any random time step tn plus 1 and perturb data point and for this timestamp, get the data point xtn plus 1. And by the way, as we saw earlier, that is a straightforward here. It is a straightforward analytical form to get that xtn. So you get that, and then you have a ODE solver from your pre-trained diffusion model that can get you the xtn plus 1 and or the noise for that, and then you add that to xtn plus 1 to get your xtn. So or in this case, you get XTN bar using phi, which is your OD solver, which in principle should be, in theory, should be very close to your XTN. And now that you have that, your objective is slightly different from the objective, the L2 loss that you saw in the previous slide. There is two things here. One is that this is the first term is still the same that you had in the previous slide, which is the origin predicted by your network. But then you have another target network where you're training, where you're updating the model parameters, which are exponential moving average compared to the student network. And this is the typical, I think, the distillation strategy, which I've not studied in detail, but anyone else who has can maybe chime in as well. But essentially, you are finding the loss based on two consecutive data points on the trajectory, the second one of which is predicted using the ODE solver. And then the F theta is learned by minimizing this objective. The only other thing is the weighting function that is applied to the objective here to account for the time step at which you are trying to learn that trajectory.
Yeah,
And I
so
don't
my
know if,
comment here,
anyone...
Dave, would be that this is not theoretically any different than just, hey, train a neural network and have it do two predictions for you know, n and n+1. Okay. But if you do that, if you only have one network, you will have higher variance gradients. And so the trick of having two networks, one of them being an exponential moving average of the other one, you'll get actually smoother gradients. And so it's not conceptually any different. If you don't understand this, it's not really critical. It's just a trick to get the training to work better. Conceptually, all you're doing is you're saying two different time steps should predict the same image. So we're just going to do the L2 loss on their predictions.
So could you elaborate on the variance part a little more?
Yeah, so there's this really, I don't know if I can say this perfectly theoretically accurate. There's this really strong autocorrelation between the predictions of the same exact neural network with its current weights that are not yet right? You're in the middle of training and you know that it's wrong in some ways. There's this real high autocorrelation between what I'm going to predict for time step n, what I'm going to predict for time step n+1. So I could get a gradient that's pointing in a very random direction. Okay. But the exponential moving average, some weighted average of recent sets of weights, are going to actually be average to being a better prediction than my current network. This is just true in general. Any model that you train, if you don't have enough compute to train it all the way to convergence, you're better off averaging like 4 late checkpoints than just using the last checkpoint. You'll get a better model in general if you do that. So this is basically saying, so if what we do is for one of them, we just have this moving average, which is like, you know, a rough average of recent checkpoints, then that actually is a better model. And so we'll get better, smoother gradients when using that instead of just always using for both terms, using the current model. Does that make sense,
That's
Dave?
a regularization technique to prevent.
Yeah. So like in the last Kaggle competition, we use this just to help with training. It is nothing specific to score models or diffusion or anything. Any neural network you're training, you can just simply throw in some moving averages, and you tend to get smoother gradients.
With less
The
time.
other thing you could
Understood.
do is you could have like a massive batch size, which probably doesn't work very well because images and everything are pretty big, and so you're like already probably needing a lot of GPU memory. But if you want smooth gradients, you could also say, oh yeah, I'll just use batch size 16,000. The moving average trick is a lot easier to implement in practice than to have ginormous batch sizes.
So I want to say it's 8 o'clock Pacific time right now. I have maybe 5 or 6 slides more. If people understood this algorithm of what it is trying to do, I mean, this is from the paper where they did the distillation, and it's just the same thing that I said here in words from the paper and in the actual pseudocode form, if you may. I mean, they are of course updating theta, which is the student network over here, and the target network is more smooth learning rather than the continuous learning. And they also have this decay factor of how much of, I mean, just like EMA, right? So the decay of how much of the student network they are going to bring in the target network as they go for further regularization purposes. So this is the distillation-based consistency model. And they compared to other distillation-based models. There was, I mean, if you read the paper, they talk about that even the distillation models had a lot of drawbacks, and the best in class over there was the progressive distillation model, which had worked in 2 steps, or 1 steps had FID score of 8.34 or 5.58, and of course they beat those for this data set, CIFAR-10. And what you see above are the best in class, if not best in class, definitely good solvers. With 10 steps, you get something like 5.94 FID, or maybe the 4.17. So they definitely saw some good results on a CIFAR-10. But as you can see, they took a lot of the other non-distillation based or non-consistency model based models have a lot of function evaluations, the ODE solver steps, if you may, right? And then they get this number. But with the consistency models, they get with 1 or 2 steps, they get pretty good FID scores. Now, CIFAR-10 is not the best of the best benchmarks, but they had results for others as well. And then they showed that they had pretty good results compared to the progressive distillation. Again, I will skip past. It's just that, depending on number of steps you had for the generation, they always did better than any other, in this case, progressive distillation. For any loss, they did better than that. If people are okay, I can spend another 10 minutes and finish the presentation, because it's not worth going into next week, but I'll let people make that call. And I know I took longer because I wanted to go through the basic of diffusion model and the ODE, just to make sure that, we are not jumping directly to this without that background.
Why don't we continue for 10 minutes?
Okay. So that was the distillation-based consistency model. There's this other approach also, which they talked about, which in principle is basically a new class of generative models, because here you're not starting with any pre-trained diffusion model, but you're defining consistency model all in isolation. And what this does is essentially that you don't need, of course, any pre-trained model, as it says here. And it avoids they train this model in a similar fashion, but because they don't have a pre-trained diffusion model and they don't have the ODE solver trajectory, if you may, so they avoid using score model also. And they had some trick in the paper, and I can maybe point to the paper. What they did was, so they basically were able to avoid using that score model, and they leveraged some unbiased estimator. So there was no need for an ODE solver as your diffusion model, provided your XTN plus 1, if you may, right? And what they have is for any discrete time. So, and this was a discrete time approach. So you basically sample a random time step Tn plus 1, and for a corresponding data point, you inject the noise to it, x plus tn plus 1z, right? And you minimize the following objective, where the objective for the model that you are training is x plus tn plus 1z, which is the noise at tn plus 1, minus stop grad x plus tnz tn. So you are predicting the origin, which is x, right? So with this and with this, using the same model, and I think stop grad, is that the distillation trick again, Ted?
Yeah, you're only learning from time step tn plus 1. You're not learning from time step tn.
Okay, so you are basically, yeah, so only learning from this one. So this is what we did in the other one for learning. So and you are minimizing this objective, and then you have this weighting function for the timestamp. And they have some proof to show that this objective is equivalent to the consistency distillation model, the previous approach one, with the ground truth diffusion models. So again, if you're working in really close vicinity timestamps, like in the discrete time approach, really close ones, and then you try to optimize this, you are able to get close to building a new model using this function at theta, which is the consistency model, but a new class of generative model, not dependent on any pre-trained diffusion model. Kind of went through this really fast, but there wasn't much more discussion. There's a lot of discussion in terms of theory and other things, but the paper also didn't have too much about it beyond, some discussion that there is some details about how the number of steps they defined, and some experimentation details. But in terms of the actual algorithm, this is what they had, and this is exactly what is defined over here in the actual algorithm 3 in the paper.
Yeah, so the key thing to understand about if you're not using a pre-trained diffusion model is that you take 2 consecutive time steps, just like we said before. Okay, you start with the tn or whatever, and you add a little bit of noise to it to get to tn plus 1. The problem is that you're supposed to be predicting along that white line, that ODE trajectory, okay? But in this case, the extra noise that you add for tn plus 1 is just completely random extra noise. It's not correlated to what white line you're on. That's why this doesn't work as well. Okay? When you do the first thing that Dave showed, the distillation, the difference between the two is a certain amount of noise, but it's noise specific to that white line, that white trajectory. Now we're just adding any old random noise, and so that's where the box at the bottom says is as the difference between time steps goes to 0, it doesn't matter as much. But we're not actually doing it in the limit. We're doing this for real time steps, and it causes problems. So this from scratch method will not work as well as the distillation thing. But in the grand scheme of things, it saves you from having to have already trained that pre-trained distillation, pre-trained, diffusion model for the distillation. So it's a huge pro in the amount of compute you need, but the results show that it's not nearly as good. So I don't know if people are ever going to actually do this unless they come up with some trick to improve it.
Yeah, and they I'm looking at the paper, page 6 of the paper, they do talk about, and I'll just read it very quickly, that again, similar to what Ted is saying, that when the time difference between the timestamps for which the consecutive timestamps or the delta goes close to 0, which is basically increasing n. So for improved practical performances, we propose to progressively increase n during training according to a schedule function. And the intuition is that the consistency training loss has less variance, but more bias with respect to the underlying consistency distillation loss when n is small, which facilitates or helps with the faster convergence at the beginning of training. But on the contrary, it has more variance, but less bias when n is large, which is desirable when closer to the end of the training. So for best performance, we should find that mu, which is the decay factor, should change along with n. And again, there are some theories, essentially, they do talk about how to improve that. But even with all of that, it is definitely not the, it doesn't meet the distillation model. And they also had formulations of what we saw for both distillation as well as the consistency training based, consistency models. We saw the discrete timestamp models, but they had formulation for the continuous time consistency training as well. Again, we'll not go into that, but they did have equivalence or the formulation for the continuous time consistency training as well. Anyhow, so this is what they had, and there are some results from the paper and they had some pictures. I'm definitely, given time, not going to go through that, but if there is maybe one or two results that we can look at, that may be helpful. But other than that, I think I'm more or less done. Only other thing is that the same authors had another paper later on, I think improved consistency models or something, where they had 4 new things brought in. I don't have the results in front of me right now, but they had better loss. Instead of using L2 or LPIPS, they had, I think, pseudo Hoover loss. They had different weighting functions for the time discretization or picking what times to use. They had some different weighting function for the different schedule, different weighting function, different loss, and one more thing, some time proposal distribution, I think. So they had some more enhancements and they got better results. One other thing that I should add is that not only like other diffusion models like this one, where the out-of-the-box consistency model that was trained using this trick worked for a lot of other subtypes of problems as well, with the zero-shot training, if you may. So it could work for colorization, image super resolution, image in painting, interpolation, single-step denoising, and the stroke-guided image generation. Again, these are some sets of problems that if people have used stable diffusion or read other papers, diffusion models are good at it, and consistency models continue to be good for those as well. And as you can imagine, once you have the trajectory known, then wherever you start from, whether black and white image, it can get you somewhere with some colors on it, because that's where it will try to get you to. So works pretty good for any of those problems as well. Let me see if I have results for the other one. I think this may be, yeah, so the right one. So CD is a distillation model and CT is the standalone model. So as you can see, we saw these results for the distillation models for 1 and 2 steps. Those are pretty good for CIFAR-10, but for the standalone isolation models, they are not as good. And the state of the art is the EDM, the Karas et al. From NVIDIA 2.4. And then same for the ImageNet 64 by 64 images. Again, they have FID of 4.7 with 2 steps and 6.2 with 1 step. And then these are other benchmarks. So CT, of course, is not there, but CD oftentimes does pretty good, in some cases, state of the art as well. Yeah, they have lots of examples here, but I'll skip those. Anyhow, so hopefully this was helpful, but it was quite a lot to cover in one meet. And this is consistency models. People may have seen enhancements to it in terms of latent consistency models, and where they work in the latent space. And there are some models out there on Hugging Face where as you are typing, the image is modifying in real time. So definitely, consistency models have made it to the products that you use out there. I think DALI 3 and others also use this. In the newest presentation, he did talk about that, but I didn't get a chance to bring that in this presentation today.
I'm sorry, Dave, did you say that they have demonstrated it using a consistency model in latent space?
Yes, so there's a follow-on paper called LCM, and let me see if I can bring that up. Anyhow, so there's a paper called Latent Consistency Model, which brought it to the latent space as well.
Okay, good.
And
Yeah, just like
That-
Stable
so-
Diffusion did latent space regular diffusion. LCM does latent space consistency model.
Cool.
Yeah, Dave, don't need to find it. I just was curious when you talk about the L2 loss in the pixel space, it kind of, to me, it makes more sense for that to be in latent space, not in pixel space. So I was just curious if they tried it in latent space.
Oh,
Yeah,
here we
and
go.
like you can do L2 loss in latent space. I don't know that you can do things like LPIPs, perceptual loss, in latent space, because that doesn't make as much sense.
It's latent,
right?
So
Right.
So here is the training efficiency that they talk about in the LCM paper. High quality 768 by 768, 2 to 4 step LCM takes only 32 A100 GPU hours for training. That is just super amazing.
Yeah.
pretty lightweight.
Yeah, and I don't know, Ted, if I always miss that. But if you have the links to those Hugging Face thing or any model which are deployed out there for inferencing for anyone to try. I remember when it first came out, I was typing and the image was changing in real time. Now, maybe it was too early for LCM, and I'm calling this LCM, latent consistency models, that they were not always the best quality, or they were not always able to capture everything about the text, but I'm assuming and pretty sure that the latest ones are doing pretty good. And on top of that, now they have the concepts injection also with LoRa and whatnot. So this whole thing is also exploding on its own. Yeah, go ahead. Ted.
Yeah, somebody shared a link with you and me, and it was nice in that it did update as you typed. So you could say, an astronaut, and then boom, you see a picture. And then as you're typing, riding a horse, boom, it updates the picture. While holding a flag, boom, it updates the picture. On the moon, boom, right? So the speed was there, but the demo that I saw, the picture quality was pretty poor. And that might be because you're running it on a free Hugging Space, whatever, A100 instance. So it had to be a smaller model or whatever.
Yeah.
But so like state of the art. So if you were some company that was gonna like generate an image that you were gonna put on a billboard, next to the freeway, you probably really, really care about quality. You're gonna continue to use a regular full diffusion model and do,
Slower,
100
yeah.
steps or whatever, right?
Yeah.
The distilled consistency model is not as high quality as that yet. But if you think about it, it's kind of crazy that you have to use a certain special architecture, you have to use a certain special training process where you do different time steps. But at the end of the day, you have built a neural network that you just input Gaussian noise and it directly outputs an image in one step, hidden iteration, no nothing. It literally just outputs an image in one step. That is freaking nuts.
Well, except that's see, Ted, that's what a GAN is, right? That's what the generative side of the GAN is. It's the GAN is trained differently using the discriminator network to drive it, kind of the space exploration. Here we're using diffusion to kind of explore that space. But in the end, we end up with F, which is the same as the generator network and a GAN.
Yeah. No, I guess you're right. I guess that's true. They both do it just like in one fell swoop.
Right.
Yeah. The way I see, I mean, I agree with Roger and Ted. the way I see this as being able to capture the signature of the image in one shot, right? So that's the part that where you get directly from 0.0 to getting the image right away. There is no, you're not like trying to explore and go there. I mean, it's there. And so I've seen some of the other papers where people use this in compression and all, where they just take the function and just like the generative function is basically captured and that's all you send. And on the other side, you basically blow up the image. So that's where I'm kind of thinking about it. So
Yeah. And it is lossy compression, of course, even though in the sense that, yes, it's a bijection, but it will be lossy compression. But with multi-step, maybe there is.
yeah.
Assuming you got really close to one of the data points that you compress, then you may get really close to it.